Welcome to 7th grade science. If you don't know who I am, my name is Mr. Morgan. Let's start talking about science. For the next 5 weeks, we are going to be discussing rocks, minerals, and fossils. So to start off with today's lesson, let's talk about rocks and minerals. What's that noise? You guys hear that? Oh, there's a concert behind me? I didn't say rock and roll. I said, let's talk about rocks and minerals. That's better. Now, I know I said let's talk about rocks and minerals, so you'd think we were going to talk about rocks first, but I really should have said let's talk about minerals and rocks, because we want to talk about minerals before we talk about rocks. So what is a mineral? A mineral is an inorganic crystalline solid. So inorganic means it's not living. If something's organic, it has carbon and is living. So minerals aren't living. And crystalline solid, we'll get into what I mean with that in a little bit. Do you remember, probably talked last year about elements and compounds? Elements are the things on the periodic table, and compounds are elements that are combined to make something new. So a mineral could be all of one type of element, such as silver, or it could be a compound, such as salt, which is sodium and chloride. Silver, diamond, and graphite are all examples of minerals that are made with one single element. In that specific example, I already mentioned silver. Silver is silver. And diamond and graphite are both made of carbon. And I already mentioned salt. It's just like your normal table salt, sodium chloride. Now, each of these minerals have a specific chemical composition that makes them different from another one. This is where it gets a little tricky though, because each chemical composition is different for each mineral, but sometimes you can have minerals that have the same chemical makeup. And what do I mean? Well, this means that you could have two minerals that have the same elements combined in the same amounts. Perfect example of this is one that I just mentioned, and that is diamond and graphite. Now, those are only made up of one element, so they're not a compound, but it still applies the same idea with a compound. Diamond and graphite are very different, even though they have the same chemical makeup in regards to what they're made of. What's different about them is the 3D structure of those elements and how they interact. And we'll get into that a little bit later, but for right now, just understand that there is a different chemical makeup for each mineral, whether that is different element or compound, or if it's the same element and compound, but a different way that the atoms are structured. Crystal structure. What is a crystal structure? Well, a crystal structure is formed when atoms arrange themselves in a pattern. This pattern is going to be regular and repeat. Now, what I mean by regular and repeat, you'll see in this image here. It essentially is the same atoms following suit in the same order, in the same way. Now is where we're going to talk about graphite and diamond. So, like I said earlier, graphite and diamond are both made of carbon. It's how the atoms are arranged that's different. Graphite lines up in sheets, or forms layers of sheets, like these two pieces of paper right here. I have one layer of carbon atoms in my graphite, and I have another layer of carbon atoms in my graphite. The carbon and diamonds, however, bond in 3 different directions. And what this does is it creates an interlocking network that makes diamonds super strong because of those bonds, which is why diamonds are really hard to break, because those bonds are so strong. Whereas graphite, which is used in your pencil, it's pencil lead. It's not really lead. It is more brittle. It's a lot more brittle than diamond because the layers just slide across each other instead of being like diamonds where they can't really do much movement. We talked about crystals. Let's talk about solids. Minerals have to be solid. You don't have liquid forms of minerals. So think of it water versus ice. Water is a liquid, ice is a solid, right? So when it's water form, it's not a mineral, but ice is a mineral. We will touch on that tomorrow during the lesson. Last but not least with this part, minerals are only formed by natural processes. So if you have ever been to a jewelry store, or if you happen to look right here on my finger, my class ring has a ruby in it. This is not a natural gemstone, natural mineral ruby that's found out in nature. Instead, it is processed in a lab. So because it is processed in a lab and created in a lab, it is not a mineral by definition because it has to have formed in nature. Now, examples of how minerals are formed in nature include lava and magma. Magma is molten rock underneath Earth's surface. When it seeps out or erupts from a volcano, it is no longer magma. It becomes lava. And lava is just molten rock that is on the outside of Earth's surface, or on Earth's surface rather, not outside it. When this magma or lava cools, minerals form from it. Some form at higher temperatures, so they form quicker, whereas others form at a lot cooler temperatures, so they take a lot longer to form because it takes time for the magma or the lava to cool. Precipitating from water. What does that mean? Well, there's a couple different things here. One of them is when water evaporates, all of the solids that are in the water stay behind. So if you have a super salty lake, or if you go to the ocean, scoop out some water in a pot, and then boil the water off, all of the water will evaporate, and all you'll have left is the solids that were once dissolved in the water. So in the example of the ocean water, one of the compounds you'll have left behind is salt, specifically sea salt. Another way that minerals form from water is just when they're traveling through caves or different rock beds, and they're leaving behind some of the solids that are in them, and then eventually over time those solids build and build and build, and then you end up with things like geodes where you have little streaks of mineral through rock. And another way that another natural process of mineral formation is when certain rocks are exposed to high pressure and high temperatures. One specific example that you're familiar with, and we've talked about a little already, is diamonds. When coal is exposed to high temperatures and high pressure, it can lead to the creation of a diamond, which we'll talk about coal a little bit later when we're talking about rocks. Up next, we are going to talk about the physical properties of minerals. So minerals have different physical properties that are used to identify them. Lots of minerals have different colors. Like I talked about the ruby, the color's red. But you can't always use a color to identify a mineral. And a perfect example of this is pyrite, or fool's gold. And it's called that because it looks just like gold. So if you happen to be panning in Alaska for some gold and you find some, you'd think, oh man, I struck gold. You go get it checked out, turns out it's fool's gold. It's not valued anywhere near the amount the gold is. So like I said, color is not a good way or an easy way to identify minerals. Besides minerals looking like each other because of their color, you have different minerals that can form in different colors. One good example of this is quartz. And in tomorrow's PowerPoint, you will see examples of quartz and the different colors that they can be. A more reliable way to identify minerals is using streak. Streak is the color of the powder of the mineral. Now, this color is often very different than the overall large sample. I believe pyrite, fool's gold, has a streak color of black, which you wouldn't never expect because you're looking at it and it looks gold, shiny gold. To test this, you do what's called a streak test. It's where you take a mineral and you scrape it across an unglazed porcelain square. And the reason that you are scraping it across a porcelain square is that the porcelain is often stronger than the mineral itself. So the mineral will leave behind some powder as it's kind of breaking down as you scrape it across. After streak, we have luster, which I've talked a little bit about, but you might not have known. Luster is the way that the light reflects off of the mineral. So is it shiny? Is it not shiny? Or varying levels thereof. You have two main categories and then different subcategories of luster. So the two main categories are metallic and non-metallic luster. Metallic luster is kind of what it sounds like. Does it look like a metal? Is it shiny and have that metallic sheen to it? Non-metallic luster gets a little more complicated. Essentially, it does not look like metal, but there are different types. Along with these different types, they each have their own characteristics. So here are a few examples. You have adamantine, which is sparkly, earthy, which is dull and clay-like, pearly, which looks like a pearl, resinous, which is like resins such as tree sap, silky, which is soft looking with long fibers, or vitreous, which is glassy. Now, like I said, there are many different examples. Those are just the 6 that I referenced today, and we're going to reference again tomorrow in the lecture. All right, so we've talked about color, streak, and luster. Let's talk about density. So density is how much matter is packed into a certain amount of space. The more packed matter is in a certain amount of space, the higher the density. Or the less packed it is in the same amount of space, it has a lower density. Relative density, otherwise known as specific gravity, takes whatever you're trying to measure the relative density of and compares it to a substance of a known density. You can use specific gravity to measure the density of minerals by comparing the mineral to a specific amount of water. Different minerals are going to have different densities. So you could have mineral A and mineral B that are the same exact size, but mineral A could feel a lot heavier than mineral B because it's a lot denser. Continuing with our discussion of physical properties of minerals, let's talk about hardness. If you think back to the diamond, we've kind of covered hardness a little bit, diamond and graphite. The graphite is a lot more brittle because remember, it forms layers of the carbon because of the way that the atom bonds, whereas diamonds form bonds in 3 different directions, so they're a lot stronger. Hardness is the mineral's ability to resist being scratched. So if you have something that's not very hard at all, it can be easily scratched, whereas you can have something that's very hard like a diamond that scratches other things but doesn't really get scratched itself. You can test this by trying to actually scratch the mineral with something of a known hardness. Now, by known hardness, I'm referring to what's typically used by mineralogists, the Mohs hardness scale. So I'll put it here and you'll see it on the PowerPoint tomorrow as well. As you can see, talc, which you might have used talc powder, it's a white powder, or is super high on the scale, which means that it's not hard at all. Or you have diamond at the bottom, which is super hard. Up next, we have cleavage. Cleavage is the tendency of a mineral to break along certain planes. Now, I'm not talking about planes like fields or planes like airplanes. Essentially, a plane is a flat 2D surface, but in what we're talking about right now, it's just the area where it's going to cleave or where it's going to break. Now, when something cleaves, it creates a smooth surface. And this is important to remember because we're going to talk about fractures in a minute, which are different. Different crystal structures lead to different cleavages. And this has to do with the cleavage plane and where those items are more likely to break. Because of this, minerals form different shapes. And these different shapes form depending on where the cleavage planes are. So minerals of a certain type are more likely to be broken at the same cleavage plane. So that's why salt ends up forming little cubes, because the structure of the compound breaks at different cleavage points, making all relatively, well, they're all small, making all similar cubes. You can also have stuff break off in sheets, such as mica or muscovite, or you can have something like fluorite, which breaks into different octagons. Now, I mentioned fracture for like 2 seconds back there. And that's because fracture is a different type of breaking. So you have cleavage and fracture, which is how minerals break. Remember, cleavage is a smooth, clean break, whereas fracture is what it sounds like. Like when you fracture a bone, it doesn't always break nicely. And that's the same with fracture. It's how a mineral breaks without any pattern. And typically this is very uneven. Now you have different types of fractures, including rough or fibrous. Sometimes it is smooth along the fracture, other times it is not smooth and you can have jagged pieces, but essentially the most important thing with fracture is it doesn't break evenly. And the last thing we're going to talk about with physical properties of minerals is some unique properties. Some minerals are really easy to identify because of their unique properties, but the majority of them aren't. So that's why you have to go through these other parts to identify a mineral, which in a little bit, few days down the road, we will talk about identifying rocks and minerals some more. But for right now, some of these unique properties that can help you identify certain minerals are coming up here. One is fluorescence, which fluorescence, when a mineral is exposed to ultraviolet light, it gives off a bright color, essentially glowing under ultraviolet light. Fluorite, which sounds kind of like fluorescence, is a mineral that does this. Magnetism, which means that it's attracted to a magnet, is another unique property. And magnetite, just like the name suggests, is a mineral that is attracted to magnets. Radiation. So you might have talked a little bit about this before in other science classes, or heard of Chernobyl, where there was a nuclear explosion and then you had radiation left over. Radiation is where essentially there's decay of the nucleus and little particles are shooting off, and these little particles can be measured by a Geiger counter. So some minerals are radioactive, and an example of one that is radioactive is uraninite. Another unique property is reactivity. So this is different than radioactivity because reactivity is it reactive? Does it react when exposed to something else? So those that are reactive will bubble slightly when exposed to a weak acid. You don't want to use a super strong acid because you don't want to totally destroy your mineral. So you would also do a little sample to test it. Calcite is a good example of one that bubbles when exposed to a weak acid. It's reactive. And this one can be a little more pleasant or not so pleasant. But the last unique property we're going to talk about is smell. You can identify certain minerals by smell, and one common example is sulfur. Some of you may have smelled sulfur water before. It kind of smells like rotten eggs. It's not really a pleasant smell. We talked about minerals, and let's talk about rocks. No, again, I didn't say rock and roll, I said rock. There we go. So a rock is a naturally formed, non-living earth material. Now, I'm not saying that there are not rocks on other planets, because there are, but for our all intent and purposes, we are going to talk about rocks on Earth until we get to the solar system at the end of this semester. But that's a long ways out. So right now, we're just talking about Earth rocks. These are mostly made of minerals. The minerals that make up these rocks could be microscopic, which means you have to look at them through a microscope, or they can be relatively large. There could be only one type of mineral that makes up rocks, or there could be multiple types within one rock. There are some, however, that are made with no minerals whatsoever. And the example that I talked about earlier that I said I was going to talk about again, coal. Coal is organic, which means it comes from living material, living matter. Coal is a type of rock, but it's not made of mineral. It actually can make minerals later on, like we talked about with diamond. It's just important to note that while most have minerals or made of minerals, not all are. Now, rocks are named based on the combinations of minerals that they have within them and how they're formed. Remember when I was talking about how minerals form? Lava, magma, precipitating from water, heat and pressure? Different minerals form from different natural processes. Since minerals form from natural processes, the minerals that are found in rocks give us clues as to how those rocks are formed. Now, geologists, those that study rocks, group rocks by how they form. And there's three main types that we're going to talk about. And we're only going to touch on them briefly today, but over the next few days, we're going to spend more time talking about them in depth. These three major types are igneous, sedimentary, and metamorphic. Igneous rocks are those that form from lava or magma cooling. Sedimentary rocks are formed when sediments are compacted and cemented together, kind of squished together. Metamorphic rocks are those that are formed when exposed to heat or pressure. The minerals in the rock change, but they do not melt. Now, after talking about those three types, we're going to take a look at the rock cycle, because those three types of rocks can all change to one another. I'm going to have a picture of the rock cycle right here, but you'll also see it in our PowerPoint tomorrow. So you'll notice on the way the rock cycle is, there's little arrows, and these arrows are showing you the directions for the changes to occur in. Sedimentary rocks that become buried and put under a lot of pressure can become metamorphic rocks. These metamorphic rocks can then later get eroded from weathering or erosion, which we'll talk about in a little bit. But metamorphic rocks can also become igneous rocks, and they do this by melting. So when they melt, they become magma if it's under the Earth's surface. If they're melting above the Earth's surface, it's probably not natural, therefore it's not forming a mineral. After they melt into magma, they cool down, whether they're cooling as magma or cooling as lava. And when this happens, crystallization occurs. Then they become igneous rocks. Now, igneous rocks can go right back to metamorphic rocks, or they can become sedimentary rocks by erosion. After erosion, for both metamorphic and igneous, they undergo a step called sedimentation, which is where the sediment settles to an area where it can become compacted together. And that's an important step for both to become sedimentary rocks. As we talk about the different rock types, we will cover the rock cycle more specific to that rock type in more depth. That's everything I have for today. So if you have any questions, please don't hesitate to reach out. Bye.